Before we get started today, let's try this. We can see if we remember what we learned on Thursday. If you'd like to take some time to try this, go ahead and pause the recording. But there's no reason for me to delay, so let's go ahead and look at it. So on the first one, right, we're going to add hydrogen to the outside. And then we have two different products. We have the 1,2 adduct, which is the first one I drew. Then we can get a rearrangement to give us the second one. On this next one, we got the bromination, so we can add the bromine on the outside there, and we get this bromine. So the 1,2, or we can get the 1,4. Okay. Give us those two products. And then again, remember on Thursday, we talked about kinetic and thermodynamic. Kinetic is going to be the 1,2, thermodynamic is the most stable. In both of these, there's not a big difference in stability, so both of these could be the thermodynamic products. There's not an obvious more stable than the other. Okay. All right, moving forward. If you haven't done so, please start working on the homework on Chem 101. We finished up electrophilic reactions, and what I want to start today on is pericyclic. So to determine what pericyclic is, first let's look back at what we had. So we had ionic reactions, right? And the ionic reactions that we had were the nucleophile, right, with negative reacting with electrophile and leaving group. Right? And then we take two electrons, an ionic species, have that react, and we end up with the nucleophile now attached to the electrophile plus our leaving group. We also had our acid and base reactions. So if we had a proton, base, so base extracts proton, electrons go back to the anion, and we see right, so we have already covered ionic reactions. We also looked at radical reactions. And that that's where we take a radical species, one electron instead of two electrons, have that react with in this case, a pi bond. We see now that we've made a bond here, we're left with a radical. Okay. In pericyclic reactions, we're going to have concerted mechanisms the reactions are all going to be concerted with electrons moving in a closed loop. We have several main types of these, so cycloadditions. That's going to be the one that we actually focus on the most. In cycloadditions, our electrons move in a circle. and we're actually adding, right? So now we've added those two molecules to make one molecule. So cycloadditions. Electrocyclic reactions. Electrocyclic reactions, again, we're talking about electrons moving in a circle. This then results in creation of one sigma bond, and then closing up that open ring system. So we're not bringing two molecules in together, but we are changing a pi bond into a sigma bond. And then sigmatropic. The sigmatropic rearrangements. Here we're not changing sigma bonds into pi bonds, but we are doing a rearrangement. So pi bond goes out, and you can see we're going to break that sigma bond, right? So this is our three types of paracyclic reactions we're going to be looking at: cycloadditions, electrocyclic reactions, and sigmatropic reactions. The one that we're going to spend the most time on is going to be the Diels-Alder reaction. The Diels-Alder reaction, we're going to take a double bond, a conjugated double bond system, and another double bond, and we're going to get a cycloaddition. The mechanism is, as we showed before, oops, let's put an X group there. We'll explain why we need an X group soon. So pi bond, that's going to turn into make a sigma bond. Pi bond moves up, pi bond moves over. We're creating, if we want to think about it, we're creating bonds here and here. And so that is our mechanism, right? So it's just a cyclic rearrangement of electrons. It's turning, it's going to be turning two pi bonds into two sigma bonds. Okay, so the energy dynamics here is that we're going from weaker pi bonds to stronger sigma bonds. We are losing some entropy because we're going from two molecules to one molecule. But we're also going from, so if we look at entropy versus enthalpy, enthalpy is a driving force for these. If we can force it to go the other way by creating a larger entropy. So if we look at this reaction going forward, usually it takes moderate temperatures, and sometimes that's relative, but moderate temperatures to get to the cyclic. But it actually turns out I can do a retro Diels-Alder. With a higher temperature. And again, if we look at delta G equals delta H minus T delta S, right? Going from two pi bonds to two sigma bonds is favored by entropy, by enthalpy. But if we look at entropy, right, this is two molecules to one molecule, right? Not favored. in the forward. But going from 1 to 2 would be favored. And so if I increase the temperature, right, then I can get this to go backwards, right? So this reaction could unzip by increasing the temperature and increasing the entropy term in this reaction. Okay, now we got two species in here. One is the diene and the other one's a dienophile, right? And so that's just, you know, diene loving. So if we just took this one, just ethane, and had that to react to give us our cyclic with the just this cyclic, we get a poor yield. Right? So roughly about 20% yield. The reason for that is the electronics between these two species. Now, if we think about our orbitals, right, we're going to be reacting. So if you remember last week, we looked at the molecular orbitals. What we're going to be reacting in most cases for normal Diels-Alder reactions is actually going to be the HOMO of the diene. And if you remember the shading, the HOMO of the diene is going to only have one node, right? So we have the shading, and that's going to be reacting with the LUMO. So if you remember, we discussed LUMOs and HOMOs. So LUMO is lowest unoccupied molecular orbital, and for the diene, the lowest occupied molecular orbital is this one, right? And so we have one node, two pi bonds, one node, that's going to be the anti-bonding orbital. And then what needs to happen is that this needs to react with here, right? So what you can think about is that the unshaded at the top are interacting, and this is interacting, and what's going to happen is these pi interactions, these p orbital reactions, will result in the sigma bonds here, right? So we're going to be changing the hybridization to give us the sigma bonds. But to get these to react, right, if we think about our energy diagram, right, what we want to do, what we have, if we look at our pi system, right, is we are going to need to interact these two, right? So those two are the ones that we're going to want to interact. So this LUMO and this HOMO. So if we can bring those in closer proximity, closer energy levels, then this is going to react faster. The way we do that is we try to find electron-rich HOMOs. In normal circumstances, there's something that are referred to as reverse, and we want electron poor LUMOs, okay? So electron rich and electron poor. These provide, when we have this setup, this provides us a better reaction. The reaction will go at a lower temperature because my HOMO and my LUMO have closer energy diagrams. So they're going to be closer in proximity. Okay. Functionally, what that means for you, this is the reason behind it. Functionally, what that means for you is you want to have a dienophile, right? With an electron withdrawing group. And the one that works particularly well, and so this is, we'll start using the term, you'll see this EWG quite a bit, right? So the one that works really well for this is actually the carbonyl species, right? So where this X is some type of carboxylic acid derivative, right? And so X here could be a ketone. And again, the little wiggly line here that I'm doing in blue this time, that's to refer to where it's connected. So we could have a ketone. We could have an aldehyde. We could have an carboxylic acid derivatives, which then means you've got your esters. You've got anhydrides, you don't see them very much, but the other one you would see is nitriles, right? So nitrile does have that pi bond system. Now, one of the reasons that that works well is that if you think about what's happening here, is that if I have an extended pi system, so if we think about this, right, it actually means that when I go in and I put in my p orbitals that I actually have, now I'm going to be reacting with the carbonyl, not the carbonyl, we can be reacting with the two carbons, but I actually have an extended pi system. Now it includes the oxygen, right? But I have an extended pi system. So for these dienophiles, and one of the reasons they work so well is that because of this, I'm actually lowering the energy of the LUMO, not just because of the electronegative part of it, but also the fact that now I have more orbitals, and the increase in orbitals brings the LUMO closer in energy. And so we're going to be reacting this one, and it's that structure, but because we have this extended pi system, we see those reactions. So with these, we see a greater reactivity. Okay. So we can think about these as better dienophiles. So let's look at a few reactions with these. And see what those would look like. So this first one, you can see that we have this system. So let's move our electrons to help you see what's happening. You can draw in a little dotted line like this. Right, that then gives me a 6-membered ring. I move this up, right? So that means my double bond is going to be right here. And then I have my aldehyde right there. On the second one here, we'll see that we'll get, again, we're going to form the 6-membered ring. So this is going to come here, this is going to go here, that'll go out there. All right, so we end up with our double bond here. And then the thing to remember on this is that when these two things come together, right? So if we go back up here and we look at this case, right, we're going to have this molecule and this molecule coming together and reacting concertedly. That means that whatever the geometry is here, right? So this geometry is cis, then over here, this needs to be cis. So on this di-substituted dienophile, I'm going to, that will direct the stereochemistry of the Diels-Alder product. If that had been trans, so if I brought in this species, say this dialdehyde, then whenever that reacted, I would see the aldehyde going up and the aldehyde going down. So if this is trans, so if this is trans, this is going to be trans. It's a concerted mechanism. The electrons are going to come up. Now it could come from the top to the bottom in this species, so they can both be up, both be down. In the case of cis and trans, you could flip-flop which one those are, so you're not going to get enantioselectivity, but you won't get any diastereomers, right? You're going to get cis or trans. Okay. Now the other species that we need to be concerned with is our diene. Now dienes can be electron rich, but it turns out in most cases, whenever you're using something like the carbonyl species, and even a normal diene is going to work fine. But what you want your diene is that you're going to want your diene to be in the S-cis formation, right? So the S-cis formation, not the S-trans. So this one is reactive, right? And this is not reactive. So although adding an electron donating group, like a methyl group on here, our groups will donate through hyperconjugation electron density back to the double bond. That can make them slightly more reactive. What's more important in a diene is that it be in the S-cis formation. Now, S-cis is not as thermally stable as S-trans, right? So therefore, you're already kind of fighting the conformation. So one of the useful dienes are things that are already locked in that formation, right? So if we look at cyclics like this, where they're already formed into the S-cis formation, those are going to be the ones that that work the best, right? So let's look at those. What this means is we'll have to bring up some we'll have to remember our bicyclics. So here, again, I think it's important, especially on these, that you kind of look at those, right? So we could look at it flat. And if it was flat, you can think about just creating the bonds here. But if we just create those bonds there, then when we're looking at that, then that's not really correct. So if we look at the three-dimensional structure, I'm going to change it. So this is what's created with my diene, right? And let's go in and color code this. So this was my diene, right? And then what's over here, let's use the screen color here, right, is my dienophile. So this is a bicyclic compound. Okay, the importance of Diels-Alder reactions is that we are going from two molecules, right, to one cyclic, right? And we haven't seen many things to create cyclics. The other important thing is that we have a lot of stereo control. That stereo control, we already saw that if the dienophile is cis, right, then the product will be cis. So whatever the dienophile, right, we get retention. And I'll say geometry in this case, we get retention of that geometry. But we also have an endo and exo, which we'll talk about in just a second, selectivity, and we have regioselectivity. So let's look at endo and exo selectivity. With endo and exo selectivity, what we're really looking for there is, first we need to figure out what it is. So what is endo and exo selectivity? So if I take one of these cyclics, right, and I react that with this dialdehyde, the cis dialdehyde, it's going to make two possible products, right? It could make this product where the aldehydes are down, and it could potentially make, should put double bond there, and it could make this where the double bonds, the carbonyls are up. Right. So if we think about this space right here, right, kind of being folded up because of this part, and I forgot my double bond, so make sure you put double bond. So if we think about that, then this is referred to as endo, right? And this is referred to exo. So if we look at that kind of underside pinning of that system. The endo is going to be favored. The reason for this is the transition state. Okay, so whenever we're bringing these two things together, we already kind of talked about the fact that we could have this underneath here like that. So we could bring these together. This will result in an endo, or we could have brought it together like this. So if we think about our p orbitals, and this coming together, we also have p orbitals in our aromatics, right? Are on our carbonyls. Over here, right, we would have those on the outside. So in this case, in the endo case, we get both interactions between our bonding orbitals, but also between our carbonyls. So we get stabilization of that transition state through this hybridization. Over here, when we think about those p orbitals, well, we'll still get this interaction, right? But we have no secondary interaction of our carbonyls. So that means that whenever we bring these two together, we're going to get endo favored over exo. Now this is has to do with the energy activation. So we think about these two things. So we have our potential energy over here. We start, the endo has a lower transition state. So even though the exo may be more stable, right? Because if we think about steric hindrance, it is the transition state, the stability of the transition state that's driving this. Let's cover one more topic. Okay, regional selectivity. So if we think about, reacting a symmetric diene with an unsymmetric dienophile, we're going to end up, it's going to end up giving us this 6-mer ring, but there's not going to be any change, right? So it's symmetric. So we could have a symmetric diene. We could also, you could think about the example of bringing in an electron-rich substituted diene and reacting that with a symmetrical. And in this case, we haven't shown one of these yet, so let's look at this dialdehyde, this 3-member dialdehyde, right? So again, we're just going to use one of the pi bonds. And because we have one of the two symmetric, it's going to come out the same way, right? So this is when it's symmetric. So what happens whenever we have one of the two non-symmetric, right? Or both of them non-symmetric is the way to look at that. So if we take this species, right, with the electron-rich group, so that methoxide would add electron density. And here we have the aldehyde, so it's going to remove electron density, so electron withdrawing group. So this is a nice reactive pairing. Right? We're going to end up with this possibility. Plus, we would have this possibility, right? This one is our major, okay, and this one is our minor. The reason for that is our electronics of our resonance structures. So if we think about this species, right, we've got lone pairs here, and we could actually draw those lone pairs coming into that pi system, right? So we could draw this going here, that going there, and that's going to give us, oops, didn't give myself enough room. That's going to give us this potential species, right? So we have our negative on that species. If we do the same thing with our dienophile, let me correct that. So we have this. Now we can do a similar thing here. And what we can do is move those electrons up to the oxygen. That's going to then give me negative here and positive. Right? And then if I draw that up again, I'm going to have my O minus H positive here. Right? So then if I put my positives with my negatives, right? So thinking about that, that means that this species has a partial negative in this position, right? And that this species has a partial positive in this position. So if we match those up, that's how we get our major product is going to be here, where we have the two groups opposite each other. So one way to look at this, right, is that here we could look at this one as a 1, 2, 3, and this one as a 1, 2, 3, 4. The reason for that is these partial, these resonance contributors and our partial negative coming to our partial positive, which gives us the major product. Okay, so that's our regional selectivity. Okay, did a little longer on this lecture than I planned, so Thursday's lecture may be a little bit shorter, but we'll do some practice when I get back. I'll also be assigning some online homework, so please work on those.